Have you ever gazed up at the night sky, awestruck by the sheer vastness of the cosmos? In that boundless expanse, countless mysteries beckon us to unravel them. We yearn to comprehend the intricate workings of the universe, from the smallest subatomic particles to the grandest galaxies. This thirst for knowledge is what drives us to explore, to question, and to seek answers. In our quest to decipher the cosmos, we embark on a journey of scientific exploration, guided by a fundamental tool, the research hypothesis. Imagine yourself as a cosmic detective, armed with curiosity and a thirst for knowledge. You observe the universe around you, noticing patterns, anomalies, and intriguing phenomena. But observation alone can only take us so far. To truly understand the cosmos, we must formulate hypotheses. Think of a hypothesis as an educated guess, a tentative explanation for the wonders we observe. It's a starting point for our investigation, a beacon that illuminates the path toward scientific discovery. Just as detectives rely on evidence to solve crimes, scientists test their hypotheses through rigorous experimentation and observation. A well-crafted hypothesis is testable, meaning that we can design experiments to gather data and determine whether our initial hunch holds true. It's important to remember that a hypothesis doesn't have to be right. In fact, some of the most groundbreaking discoveries have emerged from disproven hypotheses. The beauty of science lies in its ability to adapt, evolve, and refine our understanding of the universe based on the evidence we gather. So, as we embark on this cosmic adventure together, let's delve into the fascinating world of research hypotheses. We'll explore different types of hypotheses, each with its own unique role to play in our quest for knowledge. Along the way, we'll encounter intriguing examples that will make you feel like a true cosmic detective, piecing together the clues that unlock the secrets of the universe. Our journey begins with a simple yet profound question. What do we want to investigate? What mysteries of the cosmos do we seek to unravel? Perhaps we're intrigued by the behavior of distant galaxies, the intricate dance of subatomic particles, or the origins of life itself. Whatever our scientific curiosity, it all starts with a question, a cosmic query that sets the stage for our investigation. Let's say we're fascinated by the enigmatic nature of black holes, those cosmic behemoths that warp space and time. We might ask, do black holes emit any form of radiation? This question, my friends, is our starting point, our cosmic call to adventure. It's the driving force behind our research, the puzzle we yearn to solve. Once we've identified our cosmic question, we can start formulating our hypothesis. Remember, a hypothesis is an educated guess, a tentative explanation that we can test through observation and experimentation. It's not about jumping to conclusions, but about proposing a plausible solution to our cosmic puzzle. In the case of our black hole mystery, we might hypothesize. Black holes emit Hawking radiation due to quantum effects near their event horizons. This hypothesis, based on theoretical physics, suggests that black holes are not entirely black, but slowly leak energy in the form of radiation. It's a bold claim, a cosmic conjecture that begs to be tested. In the realm of scientific inquiry, we often encounter a peculiar entity known as the null hypothesis. Now, don't let the name fool you. The null hypothesis isn't some cosmic void of nothingness. It's more like a starting point, a baseline against which we compare our observations. It's the assumption that there's no significant difference or relationship between the variables we're studying. Imagine you're a cosmic gardener, tending to a patch of moon rocks. You've heard rumors of a special fertilizer that accelerates plant growth in low-gravity environments. Intrigued, you decide to put this fertilizer to the test. Your null hypothesis would be, there's no difference in growth rate between moon rocks treated with the special fertilizer and those that aren't. In essence, the null hypothesis is the no-effect assumption. It's like saying, let's assume for a moment that this fancy fertilizer is nothing more than cosmic snake oil. Now, you might be thinking, why would we assume something is ineffective? Well, in science, we strive for objectivity. We can't let our excitement about a new fertilizer cloud our judgment. We need a neutral standpoint, a baseline for comparison. By establishing a null hypothesis, we set the stage for a cosmic showdown between our expectations and the reality revealed through experimentation. If our observations show a significant difference in plant growth, we might reject the null hypothesis and conclude that the special fertilizer does indeed work its magic. On the other hand, if our moon rocks remain stubbornly stunted, we might fail to reject the null hypothesis, suggesting that the fertilizer's reputation was greatly exaggerated. While the null hypothesis plays a crucial role in scientific investigation, it's not the only game in town. Enter the alternative hypothesis, our cosmic vessel for exploring possibilities beyond the realm of the null. If the null hypothesis whispers, "Nothing to see here," the alternative hypothesis boldly proclaims, "Hold on a minute, something interesting might be happening. Let's revisit our cosmic gardener scenario. Remember the special fertilizer and the moon rocks? Now, our intrepid gardener, fueled by a sense of wonder, might formulate an alternative hypothesis. Moon rocks treated with the special fertilizer will exhibit a faster growth rate compared to those not treated. See the difference? The null hypothesis assumes no effect, while the alternative hypothesis proposes a specific relationship between the fertilizer and plant growth. It's a statement of expectation, a prediction of what might happen if our cosmic concoction lives up to its hype. The alternative hypothesis is where we unleash our scientific creativity, exploring the vast landscape of possibilities beyond the confines of the null. It's about embracing the unknown and venturing into uncharted territories of knowledge. By formulating alternative hypotheses, we open ourselves to the possibility of groundbreaking discoveries, to moments where our understanding of the cosmos takes a giant leap forward.